In a number of videos in this section, I've mentioned Lindo. Lindo is a linear programming solver, essentially. And I've got quite a basic kind of version here. It looks fairly old school basic. I think this release was 2003, so it's quite old now. But you can still Lindo you can still kind of download and use. Um, So what I wanted to do is I wanted to show you what the output from Lindo is, because part of the OCR MEI modeling with algorithms specification, it expects you to be able to interpret solutions from a similar program as output. Okay, so in the exam, so they might give you like the output from something like Lindo, and then expect you to be able to interpret what bits of it mean. Now, there will be bits in the output that we don't need to worry about, and I'll point those out in a moment. And what I'm going to do is I'm going to go through the uh, LP problems that we've built within this section, and we're going to try and analyze the solutions. Okay, so the first one is this one, and it was formulate finding the shortest path from S to T as a linear programming problem. So what you do in Lindo is you type in the constraints. So you would put in minimize, so min for minimize. And then on the next line, I'm going to type 8SA plus SB plus 2AB plus 2BA plus 5AT plus 7BT. And then subject to, so ST. Then on the next line, SA plus SB is 1. SA plus BA, take away AB, take away AT, is 0. SB plus AB, take away BA, take away BT, equals 0. AT plus BT equals 1. Okay, so you type in the objective function and the constraints as you see them, and then we can go up to solve. Okay, now there is extra kind of sensitivity analysis. You can look up what that means. Some of it's quite complicated and convoluted to kind of like work through. We don't need all of it. So I'm just going to put no for that. And I'm just going to put close on that as well. So this is the information that we get. Now, already some of this I'm not really going to be too worried about answering. This bit with the slack or surplus, as you can imagine, what Lindo does is it's using a simplex algorithm to solve these problems. And it introduces slack and surplus variables in order to do that. And there's also this bit with dual prices, but we don't need to consider that either. So if you're interested in finding out what those bits mean with the dual prices, then it's just a very quick Google away. But as I said, it is quite complicated, some of the bits to kind of like understand, especially depending on the context of the problem as well. What I really want to focus in is this bit here. So what it's found is that the objective function value is 8. So that means the minimum to the problem is 8. Great. And what is it below? Well, it describes all the variables that I've used in the objective function. So SA, SB, AB, BA, AT, and BT. And because remember, these are indicator variables, the solution is, although I haven't specifically told Lindo that they are taking on ones and zeros, that is how it has optimized the solution. So SB is 1, BA is 1, and AT is 1. So they are getting picked, whereas SA, AB, and BT are not getting picked. Okay, so that is how you kind of interpret that. So we want SB, so 1. We've got BA, which is 2, plus the AT, which is 5. So 5 plus 2 plus 1 is the 8. Now, the other bit here is the reduced cost. Now, what that means is that if I increased these values by 1, so if I increased SA by 1, it would reduce my optimal solution by 5. Now, in the case of this, because we are minimizing and we've got 8, that doesn't mean I'm reducing 8 by 5 to get to 3. What it means is that if I forced SA, so SA had to be picked, then the minimum would then be 5 on top of the 8 that I already have. So it would be 13. So the shortest path, if I force SA to be included, would be 8, and then you can see that it's going to be AT is 5. So 8 plus 5 is the 13. Whereas if I force AB to be included, so AB, then it increases the total by 4. So that means that the minimum would then be 12. So how can I get 12 from this? Well, what it would have to do is go SB, which is 1, BA, which is 2. That's got me up to 3. Then AB is another 2. That gets me up to 5. And then plus 7 would get me to 12. Okay, so that would be the minimum if I forced AB to be included. If I forced BT to be included, then it would reduce cost by 0, because actually there is a quick, there is another way of getting the objective function of 8, which is just doing SB plus BT. So you'll notice that, this is a good one to start with to analyze what this information is showing me, because essentially there are two possible solutions. And because it's using simplex algorithm, it just has homed in on one of the corners of the feasible region first. And it gives me the first one it comes across that solves the problem. It's not going to show me all of them. Okay. So that is my interpretation of this Dijkstra's problem. Okay. So let's go on to another problem. So this was the first of the longest path problems that we looked at, and it used the same network as we had with the shortest path one. So all I need to do is add in this extra constraint and make sure that instead of minimize, I am now maximizing. Okay, so I'm going to add in the extra constraint. AB plus BA is less than or equal to 1. And then go up to solve. Nope, and close. Okay, so what it's giving me this time, so again, I'm going to ignore this bit at the bottom. We've got an objective value function value of 17. So the longest route through is 17. And that's using SA, so 8, and AB, 2. So it gets me up to 10. And then BT, 7. So that gets me up to 17. So if I forced SB to be used, that would reduce my value by 5. So if I forced SB to be used, then I would have 1. And then remember, I'm looking for the longest path. So what would I need? That would have to get me down to 12, wouldn't it? So it'd be 2, 2, 7. Okay, so that would now be the longest path. So it's actually going along SB, then BA, AB, and then BT. That would get me to 12. And that's 17, take away the 5. So rather than adding the reduced cost on now, we are maximizing, so it would reduce the 17 by 5. Likewise, BA, if I forced BA to be used, it would reduce it by 4. And if I forced AT to be used, then it would reduce it by 0, so it wouldn't change anything. Okay, so where's that coming from? Well, what would it be? 8, 2, 2, 5. Okay, you could do it that way instead, and that would get you the 17 as well. So there are a couple of alternatives there. So that's how we can interpret the objective function or the LP output in this case. Let's look at another one. So this was the first example of finding the maximum flow from S to T. So this is a network flows problem, and I've typed in my linear programming problem. So maximize SA plus SB subject to, and here are the constraints as we had. So let's go up to solve. Nope. You might also kind of like be interested in, sometimes you see these iterations. So that's how many iterations of the simplex algorithm it's gone through. So what do we have here? Well, the objective function value is 13. So that's telling me that the maximum flow through the network is 13. SA is taking on 8. Okay, so that's going to be at maximum capacity. SB is going to take on 5. BA is going to take on 0. And AB is going to take on 0. So both of those are 0. AT will be 8. And BT will be 5. So we've got 8 flowing into A, 8 flowing out of A. We've got 5 flowing into B, 5 flowing out of B. So 8 plus 5. So we're maximizing SA plus SB, and that gets me the 13. Okay, and likewise, I could have changed this, as I suggested in the video, to maximizing instead AT plus BT. If I get rid of that, solve. You'll notice that it's still 13, and it's still got exactly the same values. AT is 8, BT is 5, SA is 8, SB is 5, BA and AB are both 0. Okay, so that is how we can interpret this for a network flow problem. So here was the problem that we had with the critical path analysis alternative. So a different way of doing it rather than using the longest path method that we saw earlier. And what I've done is I've typed in the linear programming problem. So I've got minimized T, subject to, and I've got these constraints. Now I've purposefully not moved everything onto the left-hand side because I just want to show you what happens. So I'm going to go up to solve. And this is an error code that I'm getting from Lindo. It's saying expecting a right-hand side value, the following was interpreted A is greater than or equal to. So essentially, it had a problem when it got to A is greater than or equal to B plus 13 because it wasn't expecting any variables to be on the right-hand side. So whenever I type these into Lindo, I must put them in the usual form of having the variables on the left-hand side. Let's correct that. Right, now it should work. So solve. Right, no problems this time. And it's saying the objective function value is 38, which matches with what we had when we did the forward and backward pass in the video. So the value at T is 38. The value at B is 5, and the value at A is 18. And those values match up with what I had in the video. So let's take a look now at a matching problem. So here we had the matching problem from before, and I've typed it all into Lindo. So maximize this objective function subject to these constraints. So solve. Nope. Close. Okay, so what does this mean? Well, the objective function value here is 4. And what that is telling me is that I have matched 4 workers to 4 jobs. So that's all worked out. And it said, right, here is the first solution. So there may be more than one solution to this. But let's interpret this. So we've got A1 being chosen. So we've got A1, we've got B2, we've got C3, and we've got D4. Okay, so that is a perfectly valid solution. And as I said, there may be more than one solution to it, but Lindo will only output one of them. So that's how we can interpret a matching problem from Lindo. So here we had our allocation problem, where we had some machines had to be matched to some tasks. Each machine had to be picked and each task had to be completed, but only one machine could complete each task. So this is what the problem was, and here is our minimizing objective function subject to these constraints. So let's see what Lindo makes of this. Okay, so it's telling me the objective function is 13. So what's that telling me? So A2 is being picked. So machine A with task 2 gets me a value of 2. We get B being matched with 1. So B being matched with 1 is 7. So we had 2 plus 7, so that gets us to 9. Then we've got C3 being picked, so C3 is 4. So that's 9 plus the 4 gets me the 13. Okay, so that is going to minimize the total cost here. So it's also saying that if I force machine A to do job 1, then it will reduce the cost by 4, which means that my minimum value will now be 17. Okay, because I was minimizing, reduced cost will just worsen the situation. Okay, so 13 plus the 4 will get me up to 17. And if I force B2, so machine B to do job 2, it will increase it by 4. If I force machine B to increase to do job 3, then it will take me up to 15 because it will add on 2. And if I force machine C to do job 2, it will increase it by 5. Okay, now it's also showing that there are going to be more than one optimal solution here. So the fact that I can have machine A doing job 3 and it's not going to change the cost of 13, that's essentially telling me that there's going to be more than one solution here. So we're now going to take a look at the final problem, the transportation problem. And I've typed it into Lindo. Okay, quite a long one, this one. Hopefully I've typed it all in correctly. Just doing a quick double check. So let's have a look and see what it makes of it. So solve. No. Close. Okay. So the objective function value is 7,732. So in this problem, we had the warehouses had the availability and the shops had requirements, but the availability, so if warehouse A had to ship one of its boxes to shop 1, for example, then that would cost 83 per box. And then if it shopped 2 to shop 2, then that would be 80 each, so another 160. So it's essentially all the warehouses have to deliver to get rid of all of their availability to the shops. And yeah, so the minimum that can be done in is 7,732, which could represent pounds, for example, depending on the context of the problem. Okay, so what it's saying is that warehouse A should deliver all of its 20 boxes or 20 items to shop 3. So all 20 should go to shop 3. And you probably might pick that initially because it's the least of those 4 numbers there. B, so warehouse B should ship 15 to shop 1. So 15 to shop 1 and 20 to shop 2. Whereas warehouse C should ship 8 to shop 2, 10 to shop 3, 22 to shop 4. Now, if you wanted to force 1, so if you wanted warehouse A to ship 1 unit, So that would just be increasing by the value by 1, because we're not looking at indicator variables here now. If you wanted to increase that just by 1, it would reduce the cost by 13. So it would add 13 onto this. Okay. And likewise, if you wanted to force warehouse A to ship 1 unit to shop 4, it would increase this by 16. Okay, so that's how we can interpret the Lindo outputs for each of the problems that we have dealt with in this section.